Let's take a look at section 6.2, bisectors of triangles. So we're going to look at our triangles and two types of scenarios. One where we bisect each side of a triangle, then the other one is going to be when we bisect the angles of each triangle. Let's start off and take a look at a few terms here. The first one, concurrent. What that is when three or more lines, rays, or segments intersect at the same point. So let's say if I draw a figure right here on the side, or I could just draw just three lines. Got line 1, line 2, and line 3. And so when three or more lines intersect at the same point, which would be right here, we would say that these three lines are concurrent, and this point is actually your point of concurrency, which leads us to our next term, which is the point where the intersection of lines occur. So it could be lines, once again, segments, rays, etc. Three or more, they all intersect at one particular point. The next term is that we're going to look at is circumcenter. And that is when three perpendicular bisectors are congruent. Okay? When three perpendicular bisectors are concurrent. We'll take a look at pictures and diagrams of that in a little bit. And then the last term right here is incenter, which is the point of concurrency for any triangle. The incenter always lies inside the triangle. And so you can see I put in bold that the incenter always lies inside the triangle. The reason why I say that or highlight that is because the circumcenter can actually be in three different three different places in relation to a triangle, and we'll talk about that as we take a look at theorem 6.5 right now. So in theorem 6.5 we have the circumcenter theorem. I put in parentheses perpendicular bisector. So make sure to help you remember circumcenter, think perpendicular bisector. And if I am bisecting a side, well, you're going to split a side into two congruent pieces. So what the theorem says here is this. The circumcenter of a triangle is equidistant from the vertices of the triangle. So it says if PD, PE, and segment PF, okay, are perpendicular bisectors. So once again, PD, let's go ahead, I'll highlight that in blue. We got P to E and P to F. They are saying that if all of these segments are perpendicular bisectors, okay, and what you also need to have note right here is that in order for me to understand that these are not just perpendicular, but they bisect sides AB, we'll go ahead and put the little tick marks here. BE is congruent to EC, and FC is congruent to FA. All of these right here need to be known in the diagram. Then what they're saying here is this, that the distance from P to A, I'll highlight that in green, P to B, and P to C, those are all congruent or equal to each other. Okay, so there's a lot of things going on. Once again, you start off. I know that I have perpendicular bisectors. If I know I have perpendicular bisectors, then I can say that from the point of concurrency, okay, because what happens is that all of these perpendicular bisectors, they meet right here at point P, that point of concurrency. And so right here, this segment, P to A, once again, P to B, and P to C are all equal. Not PD, not PE, and not PF. Those are not congruent to each other. So, as we move along right here, the circumcenter can be found in 3 different places, and it depends on the triangle. Okay? If you have an acute triangle, the circumcenter will be on the inside. If you have a right triangle, then the circumcenter will be on the outside. And if it's an obtuse triangle, if it's a right triangle, it's actually on the triangle. And then if it is an obtuse triangle, then the circumcenter will be found on the outside. Now, if you take a look on page 311, you will be able to find diagrams that I'm going to show you right now. So look at here. This is page 311. We have our triangle, and it's being circumscribed. So remember, think of circumference being like the outside part of a circle. So when we think of circumcenter, let's think about the outside of the triangle. It's being circumscribed or surrounded by the circle. And then on the inside right here, we have an acute triangle. There's your circumcenter. In a right triangle, it happens to be on the triangle itself, and you can see right there, it is on the what we call the hypotenuse of the right triangle. And then in an obtuse triangle, remember, which is a triangle greater than 90 and less than 180, it's an angle greater than 90 and less than 180, but obtuse triangle is greater than 90. You can see that the circumcenter is on the outside. Right, so these 3 concepts are very important to know. So make sure you remember, acute inside, right triangle on, and obtuse will be on the outer part. Once again, you can find that on page 319. All right, let's go take a look next up at theorem 6.6. We have the incenter theorem. And this term right here, if you can remember, incenter, it will be the angle bisectors. So meaning this, it says that AP, BP, and C to P, all of these segments are bisecting their corresponding angles. Okay, so you can see something like this so that you know that we have these angles are being bisected. So what that tells me here is this, that from P to D, P to E, and P to F right here, all of those happen to be congruent. Okay, but they must be, if you take a look, they've got this right angle. Okay, so these right angles right here, they're not perpendicular bisectors, they're just perpendicular to that side. And so all of these pieces or segments, which would be the right term, they are all congruent to each other. Therefore, PD is equal to PE, which is equal to PF. So let's put it all together. Let's take a look on these problems 1, 2, and 3. So it says right here, N is the incenter of triangle ABC. So if it's the incenter, remember, we know that we have some parts or segments that are congruent. In number 1, those segments happen to be from like N to D, right? Why N to D? Because it is perpendicular. Remember, the shortest side or length from one side to a point is the perpendicular. So what we'll do right here is, now that I know that these segments are all perpendicular to each other, it says up here we know what ND is. ND should be equal to NE. And don't forget, that is because of the incenter theorem. So let's take ND, which is 2x minus 5, and set that equal to negative 2x plus 7. And then let's go ahead and solve for x right here. I'll add 2x to both sides, so I have 4x is equal to 12, because I add 5 to both sides. We'll divide both sides by 4, and x is equal to 3. I didn't find the answer, because what they said is let's find NF. But if you look up here, they don't mention anything about segment NF. Remember, it's okay, because remember, ND, NE, and also right here, NF, they're all equal because N is the incenter. If there's no mention of point N being the incenter, then I cannot make that assumption or distinction. So let's go ahead. All I need to do is take 3 and plug it into one of these equations. And so how about we'll plug it into ND. So we got 2 times 3 minus 5. We've got 6 minus 5 right there. And this right here equals 1. All right, so NP ends up equaling 1. And we could say that that's because of the substitution property. We could substitute, or we could say transitive property. Right, if A equals B, B equals C, then A equals C. All 3 segments are equal to one another. All right, perfect. Let's take a look at number 3. Let's skip number 2. So they said that NK is equal to x plus 10, NL, right here is negative 2x plus 1. So remember, because N is the incenter, I know that these 3 segments, which are perpendicular to the incenter, that tells me that they're all equal. So I could start off and go ahead and put that NK is equal to NL. X plus 10 is equal to negative 2x plus 1. Let's go ahead, I'll add 2x to both sides. And then right here, let's subtract 10. So I got 10, or 3x is equal to negative 9. And x is equal to negative 3. All right, so we got negative 3 right here. Let's go ahead and plug this into NK and end up with negative 3 plus 10, and N to K is equal to 7. Well, that tells me that NM is equal to 7, because once again, for all these 3 segments right here are congruent to each other. All right, so pretty easy. But you got to know what that theorem is of incenter. And don't forget, the incenter will always be on the inside of your triangle. So let's take a look next up at number 4. They don't really tell you much. You've got to determine by looking at the diagram whether the points happen to be the circumcenter or the incenter right here. So let's look at number 4. I'm looking right here. I've got perpendicular P to D, and it looks like it's bisecting A to B. Let's take a look at the next segment, P to E. Perpendicular, it also bisects A to C. I see a trend. So what does that tell me? Hopefully you realize that we are dealing with the circumcenter here. So if I have the circumcenter, because we have perpendicular bisectors, right? Look, all these perpendicular bisectors right here. Well, what that next tells me here is this, that we have certain parts that are congruent. What are those parts? A to P, B to P, C to P are all equal to each other. Okay, so remember, at this point, we should be able to realize that AP is equal to BP, which is equal to CP. So look, we have right here 13. Well, this segment is 13, then so are all the others, right? If AP is equal to 13, so right here happens to be A to P, or we could say, we figured it out right here, A to P, or P to B is 13, so we could put 13 right there, and it would be same thing, equal to AP, which is also 13. All right, so there's your answer. Let's take a look at number 5. Give you a moment. Take a look at that diagram. Do you see perpendicular bisectors or do you see angle bisectors? I see angle bisectors right here. Look at angle D, angle F, and angle E. What does that mean? We have incenter. What does that tell us? We have the incenter. Then we have P to T, P to S, S to U are all congruent to each other. So if P to U is equal to 8, then P to S also needs to be equal to 8 due to our incenter theorem. Let's look next up at number 6. We look at G to E. What's going on here? Look at where point G is. It actually has to be all the way on the outside of the triangle. Well, when a point's on the outside of the triangle, hopefully you recall now, remember we went over that list of 3 different places where the circumcenter can exist. Remember, it's in your page 311. It could be on the outside, inside, or on the triangle itself. Well, this triangle right here, triangle EDF or DEF, that looks like an obtuse triangle. Guess what? That happens to be the circumcenter. Take a look. I've got right here perpendicular bisector. We've got perpendicular bisector right down the middle. Perpendicular bisector. So what that now tells me is that we have certain segments that are congruent. G to D right here should be congruent and equal to G to E, which is also congruent, which we don't see, but it would be equal to G to F. So if G to D is 10, G to E is 10. And there you go. Last one, or at least for this set, number 7, N to F. Take a look at the diagram. What do they give you? Looks to me right here, we've got angle bisector. And with the angle bisectors, that means we have an incenter. Look at angle A, bisected. Angle C, bisected. Angle B, bisected. So, right here, right in the middle, we have our incenter. So that's telling me that particular segments like NF, N to E, and N to D are all congruent. So NF right there happens to equal 2, because NF is equal to NE, which is equal to ND. There you go. Lastly, let's take a look at number 8. We want to find the coordinates of the circumcenter of the triangle with the given vertices. Remember, to find the circumcenter, you must look on, figure out, well, what does circumcenter mean? we've got perpendicular bisectors. If a triangle has sides that are horizontal and vertical, it makes things so much easier because then you can count where the middle is of each side. So let's look right here. At -2, -2, we have point A. At point B, we have -2, +4. 1, 2, 3, 4. There's point B. And point C happens to be at 6, 4. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. There's point C. So remember, with vertical and horizontal lines, it's real easy because then we just need to drop a line down the middle. We can count, or what you might have to do, guys, is use the midpoint formula if you cannot determine where the middle is. Okay, so if I need to figure out where's the middle of A to C, look, you can't eyeball it. What you can do is use that midpoint formula. So that right there is a key skill that you're going to need to use to help you solve some of these problems if you don't have any vertical or horizontal lines. Luckily, we do have some. So let's look. If I know that B to C, let me count this out. 1, 2, 3, 4, 5, 6, 7, 8. That length is 8. Half would be 4. So how about I count 4 units from point B going to C right here. And so we got 1, 2, 3, 4. 1, 2, 3, 4. That would be the middle. Perpendicular to a horizontal line would be a vertical line. So how about, let me just draw it out right there, perpendicular bisector. Let's do the same with B to A. 1, 2, 3, 4, 5, 6 is the entire segment. Half of that would be 3. So let's count 1, 2, 3. There's the middle. And let's go ahead and do this right here. Perpendicular. Guess what? That right there is where the two lines intersect. I didn't draw a line AC very well, but it's going to go through there. Now, do I actually need to figure out A to C? Not really, because I already know where it's at. It happens to be right here. The circumcenter happens to be on the triangle. Well, why is that? If you take a look, we have a 90-degree angle. So we can go ahead and say, find the coordinates of the circumcenter. It happens to be at the ordered pair 2, 1. And there you go. We now know bisectors of triangles right here.